Hello, this is Professor Kamen with Machining 1319, and this is your video presentation for additive manufacturing. Now, this is one of my most favorite subjects because we talk about some of the latest technologies that are being used in the manufacturing process. We're going to start with a little bit of a history of how additive manufacturing came out, and then we're going to talk about some of the most common processes used in additive manufacturing, and then we're going to end up with some of the latest technologies that we have going on today. It's very, very exciting. Let's get started. So additive manufacturing actually started as a process called rapid prototyping. Now the question is, what is rapid prototyping? And so it came about as people are trying to design and to create different designs and different products that will answer and solve different solutions. You needed to make prototypes. But what happened was it took a really long time to make these prototypes. So rapid prototyping was an effort to make up technologies or to create technologies that would use computers that would rapidly produce a single part. So these were focused on prototypes. So they didn't have to have the material and mechanical properties of the actual part, but you did want them to somehow simulate, somehow represent the dimensions of that part, so you could feel it and you could start making different design changes from that point. But you want to do this kind of on demand, because what would normally happen is that you would design something and then you would have to set up all this tooling, set up all this machining equipment, and then actually make it. Sometimes it would take a week, sometimes it would take several weeks just to make a prototype. And so the effort was to make a rapid prototype on demand. And this is without the use of traditional tools or dies. So what were some of the advantages of this rapid prototyping process? Well, first of all, you could have these physical models or prototypes very, very quickly, and you can have them in hours, and that could allow you to continue to iterate and make it better for design effectiveness. And that was a whole driving point to this rapid prototyping. Now, also, the prototype itself can be used in subsequent manufacturing operations. So that was called direct prototyping, in which case, say, for instance, you made a prototype and you made it within a few hours. Then later on, that prototype could be used as a pattern to make a mold in a casting process. And so that prototype itself is used in later on manufacturing operations. So that's direct prototyping. So that's one of the advantages there. Then also rapid prototyping could be used as a faster method of creating tooling. So you can actually create tooling rapidly that could be used in the manufacturing process as well. So that was called rapid tooling. And finally, rapid prototyping, this is a kind of the holy grail, is trying to work towards to be used for direct manufacturing of parts. So that means that you use a rapid prototyping process to make the parts itself, okay? And that's called rapid manufacturing. That's what, of course, it used to be called. Nowadays, it's a part of the additive manufacturing process. So I do want you to be aware of there are some specific limitations that we still have with rapid manufacturing, which is now kind of morphed and evolved into additive manufacturing. And that's that the time it takes to produce each individual part is still fairly long for large production runs. So you have sometimes it takes maybe a day, 2 days, maybe several days to make one part. Nowadays they're starting to enlarge that a little better, but essentially what they do is they have lots of machines. So if you're a company that produces 3D printed parts or additive manufacturing parts, what you do is you have a lot of machines and you run them in parallel. And you have to do that because it just takes a long time to create these parts. Also, another limitation is that we don't really know what the long-term performance of some of these parts are. And when we talk about long-term performance, we're talking about not just a couple of years, but we're talking about 5 years, 10 years, 15, 20 years out. How are these manufactured parts done by rapid manufacturing or additive manufacturing? How are they going to perform when we talk about fatigue and wear? So that still has yet to be established. Now, most rapid prototyping processes nowadays are created layer by layer. That's where we get the term additive manufacturing from. But in the beginning, rapid prototyping processes were really subtractive. Okay, they were very, very similar to machining processes. The only thing that made them rapid was that they were using different types of materials, using soft materials that allowed them to machine them a little bit faster. So these are processes that still remove material from a workpiece. Okay, and like I said before, it was similar to machining and use similar processes, but of course they are made faster when you use softer materials. So we were using polymers and wax down instead of metals, and harder materials just took longer. So that's how that rapid prototyping first started out at. And they use different machines, such as these desktop building machines. In fact, when I was in grad school, that's about 15 years ago, we had kind of desktop building machines like this that made prototypes out of wax, and we use those to help us design artificial knee implants, actually. This is another example of a desktop rapid prototyping machine. So we've kind of moved from that rapid prototyping where we're just taking machining and making it smaller and using softer materials to make it rapid, where we're actually going to an additive process. And an additive process is defined by a process in which you use CAD software, so that's computer aided design software, to take a design and then separate it into layers. So when we separate that design into layers, now we allow that particular part to be built up in layers. So the machine is going to lay down layers of the material and build it up. So that is the additive manufacturing process. That's the basic rundown of it. Now, there are lots of different additive manufacturing processes. We're going to go through some of the most common processes, and towards the end, we'll start talking about some of the later processes that are actually producing direct prototyping or direct manufacturing, rather, of metal parts. The first manufacturing process, additive manufacturing process we want to talk about is called fused deposition modeling. And I want you to pay attention to some of the unique characteristics of these processes because they will be on your test or they will be on your final exam. So in fused deposition modeling, what happens is you have a gantry robot, and a gantry robot is just a robot that works on an XY axis. So it goes left and right and it goes back and forth. Okay, that's a gantry robot. Gantry robot has an extruder on it, an extruder head. And then again, moving in two principal directions, so left and right, so your X and then your Y axis there. And it does that over a table, and this table can be raised up and down and lowered as needed. And this extruder is heated and then extrudes a polymer filament. So you have a polymer filament that's in the solid form, and when it goes through that extruder head that's heated, it softens up a little bit and allows it to be laid down on that table. The extruder polymer, it bonds to itself. So it bonds to the previously deposited layer. And again, layer by layer is what describes your additive manufacturing process. So there are some unique characteristics of your deposition modeling. Okay. And remember, that's fused deposition model. Okay. Fused because it bonds to itself. So what do we have? So we have build material and we have support material. A lot of times when you see the additive manufacturing process, you will see build material and support material because your build material is actually the part, but there are some features of the part that may have to be supported as it's being manufactured. And so that's why you have this support material spool here. Now, this spool feeds in and then it goes through this extruder on that gantry. And then here's a closer look at that. As the polymer material goes through the heated extruders, it softens up a little bit and allows it to be deposited in layers at a time. So that's the fused deposition modeling process. So what are the advantages and disadvantages? So you can create durable parts with high accuracy, but when we talk about accuracy, you have to look at different planes. So your layer size can be up to 5 thousandths or maybe a thousandth of an inch in accuracy in the XY plane, but you have to be careful because that's still not that accurate. You can see kind of like a stepped surface due to that layering process, and so it's still not small enough to where you don't see that stepped layering. Okay. Now, this advantage is that it can just take a long time to do these parts. So if they're not small, if they're a lot larger, you can have maybe 8, 9 hours, a half a day sometimes in creating some of these parts. And also, like I said before, you have that stepped surface. If you have a curved surface, you can see that stepped artifact there. So let's go ahead and look at a video talking about fused deposition modeling process.
A rapid prototype starts as an STL file generated from a 3D CAD program. The model is oriented within the computer exactly as it will be built in the FDM machine. Orientation may affect build time, strength of features, and support material generation. Once the model is oriented, the software divides the model into evenly spaced planar sections, each measuring as small as a few thousandths of an inch. Supports are then generated for overhanging sections. Each layer consists exclusively of non-overlapping and non-intersecting curves. Tool paths are created in the regions indicating whether the FDM machine should extrude model material or support material. Once the tool paths controlling the XY movements have been generated for all layers, a file is created and sent to the FDM machine. Inside the heated build envelope, the model material in filament form is heated to a less viscous state for extrusion. The model is built layer by layer from the bottom up. On each layer, the extrusion tips follow the tool paths calculated in the computer. After each layer is completed, the plate drops and a new layer is added. When the final layer is complete, the modeled part can be removed. After support material is removed, you are left with a strong, durable, and functional prototype.
Okay, so that was an explanation of the process of fused deposition modeling. And we are going to, let me get to where I want to continue moving here. We have another video that talks about that. Now, I'm not going to watch this whole video. Again, this presentation is going to be posted on D2L, so if you want to watch the entire length of the video, feel free to, but I'm going to start it off and then cut it off there. But to give you another perspective on the fused deposition modeling process, that's what this is for. So let's go ahead and watch it.
The biggest advantage to fused deposition modeling, hands down, is the material. Many 3D printing technologies such as stereolithography, SLA, or even our own objet machines use a UV cured material that simulates plastic. This actually is plastic. So while a UV cured material can be prone to things like warping or breaking down when exposed to UV rays such as sunlight, this will not. The material at hand is an ABS thermoplastic, and with all of these different hobbyist machines entering the market, it's very important to know that not all ABS is alike. Even within Stratasys, the guys who manufacture the fused deposition technology, they have varying levels of material based on how sophisticated the machine is. Things like tensile, impact, and flexural strength will vary depending on the machine at hand. Our material is engineered for the Fortis production systems, which Stratasys advertises is 40% stronger than their standard ABS. So the important takeaway point is not all ABS is alike, by far, and we encourage you to look at the material specifications before ordering an ABS part. The biggest disadvantage with FDM is the speed. FDM machines are slow. A decently sized part could easily take a day or longer to build. This is one of the reasons that a lot of companies don't even offer FDM. It's an absolutely phenomenal product, and it can be very cost effective. But unless you have a whole fleet of machines like we do, it's just not economical for people because if they get a couple jobs, the machine is booked for weeks. With that, one of the things that you almost always have to budget with FDM is time. Knowing that.
Okay, so we're going to start right there. And you heard several things in that video. One of the main things he was talking about towards the end is how long it could take to make some of these manufactured products in additive manufacturing. Sometimes it could take a day. And so that is, as I mentioned before, one of its major limitations. But he also mentioned too this ABS, which is a type of plastic material that's very strong, that's used quite a bit for prototyping. So ABS is just a common material that's used. That's why he says it so much. Now let's go ahead and continue on with our next additive manufacturing process. In that previous video, he also mentioned stereolithography. He compared fused deposition modeling to stereolithography and said that, well, this is better because, we don't have to worry about this UV cured stuff. So what does he mean by that? Let's look a little bit closer at the stereolithography process. First of all, let's understand that stereolithography was one of the first developed additive manufacturing processes. It was developed before fused deposition modeling. In fact, when I first started my undergrad, I know I'm dating myself, but I remember visiting one of our labs, and we had a stereolithography machine, but it was huge. It was really, really huge. You can see nowadays these have shrunken quite a bit, and so they're a lot smaller. As hobbyists, we can purchase them nowadays for a couple of $100. Stereolithography machine, maybe $300-400, but back then, $500,000. Just like about how the metal printing machines are nowadays, they're half a million. I'm sorry, $500,000. So stereolithography. So again, developed prior to fused deposition modeling. So what happens here is that you have a vat that holds this liquid, and this liquid is photocurable liquid acrylic polymer. What in the world is that? You don't have to know exactly what it is. All you have to know is that it's a liquid that cures when a certain light hits it, and that light is UV light. Now, what the previous guy was saying is that when you take it outside, guess what the sun is? The sun is UV light, and so that UV light can sometimes deform, and it can sometimes break down your stereolithography product if it's just left out there for a long time, because you're continuing to hit it with those UV beams. But that's how it's created. And so you have a laser that generates this UV beam. It focuses just on one area of that vat and then hardens it. And then you just remove the part from the vat, you clean it ultrasonically usually, and then sometimes also you cure it a little bit more by putting it in the oven. So that happens as well. You can see that this has higher tolerances up to about 5/10 thousandths of an inch as opposed to fused deposition modeling. So that's one advantage it has when compared to fused deposition modeling. So here's a diagram of the stereolithography process. You can see that you have a plate right here. It starts towards the top and then just kind of lowers down. And each time you have this UV light source or this laser that it sends down a laser, and then it hardens that particular point. And then the plate goes down again. You start with a layer. So layer by layer, it's built, then you remove it from that vat, clean it, and usually you cure it in another oven. So here's a video on the stereolithography process.
Stereolithography is a rapid prototyping process used to create parts from 3D CAD data in a matter of hours. SLA is a highly accurate additive manufacturing process and may also be referred to as rapid prototyping or 3D printing. Models created with this technology are typically used as concept models for form and fit studies, or as master patterns for molding techniques. The SLA process begins when CAD data is sliced into thin cross-sections or layers, typically about 6,000.
I just have to stop it right there, but you can see how it said that stereolithography is used primarily for prototyping, or it can be used for master patterns for other molds. And so primarily, this is a rapid prototyping process. It could be called additive manufacturing, but you're using these mostly for prototypes or using these to develop, to help you develop things for the manufacturing process. Go ahead, continue from that point.
This data is then transferred to an SLA additive manufacturing system containing a vat of UV curable photopolymer. The machine begins to build the part one layer at a time. Each layer is constructed from an ultraviolet laser that is directed by X and Y scanning mirrors. As the laser traces the cross-section on the surface of the resin, the liquid material is hardened on contact. Once a layer is complete, the build platform is indexed down to make room for the next layer. A recoater blade moves across the surface, ensuring a thin coat of fresh liquid resin is evenly spread over the object. The laser continues to trace and form each layer atop the previous layer, building from the bottom up. The completed part is then carefully removed from the liquid and separated from the platform. A chemical bath removes excess resin, and the part is cured in an ultraviolet oven. Any support structures are removed at this time. With numerous hand sanding and professional paint options available through service providers such as Solid Concepts, stereolithography has become an excellent economic choice for rapid appearance models. A wide variety of industries have embraced SLA, including medical, automotive, entertainment, aerospace, and consumer products.
Okay, you can see on that video that if you have a very, very curved surface feature, you can see there's that step surface. So there is some post-processing that's needed, a lot of hand sanding that's often done with different prototypes like that. Let's continue on. And make sure I know where I started here. All right, another additive manufacturing process is three-dimensional printing process. Now, you have to be careful because this can be a little confusing, where nowadays we call everything 3D printing. You heard in the video before, rapid prototyping, 3D printing, additive manufacturing. Now, essentially, they're all the same. They're used interchangeably. But there is a specific additive manufacturing process that is called three-dimensional printing. So that can be a little bit confusing, but let's take a closer look at what that is. Now, in three-dimensional printing, what happens is that you start out with a powder, and then similar to what happens in fused deposition modeling, you do have a print head on a gantry, but this print head on the gantry is actually depositing binder material. So it's not actually depositing the material itself, which is what happens in fused deposition modeling. It's depositing a binder material onto that powder. So this could be a powder of polymer, could be a powder of ceramic material, or a metallic powder. And this is how some of the first machines started coming about that could produce metal products and metal parts. Then a piston is lowered incrementally. So that has a similar feature as it does to stereolithography, in that you have a bed of material and then the material is hardened somehow. And then you have this piston, or you have some type of plate that lowers sequentially, giving you another layer, and then you harden again, lowers another layer, you harden again. So that's the kind of same basic process of stereolithography. Now, this is an extremely flexible kind of material and binders that are used. So you can use lots of different materials, whatever type of powder you can put in there, and then you can use different binders as well. And you can also produce full color prototypes, and that you can produce full color prototypes just by using different color binders. So here's a diagram of the 3D printing, three-dimensional printing process. You see here how you have beds of powder, and what happens here is you have two beds of powder. Here's your feed piston, and here's your build piston. And as your build piston goes down, then your feed piston goes up. You're going to have some type of leveling roller that rolls across and evens it, just like you had in the stereolithography process. And then here is your binder. Your binder comes down and it's fed, and it deposits that binder, which hardens that powder together. Now, when you bring that powder out, there's a lot of course, when you bring the part out, there's a lot of powder that's left over. And so you can usually reuse that a certain amount of times, but after that, there's a lot of post-processing that typically has to take place. Let's look at some videos that describe this three-dimensional process a little bit better. Three-dimensional printing process.
Three-dimensional printing, or 3DP, was originally invented and developed at MIT in 1993. A year later, Z-Core obtained the license and began developing the technology with its first printer, the Z402, being commercialized in 1997. Here we have the Z Printer 450, It has a maximum build volume of 203 by 254 by 203 millimeters. The 3D process begins with the creation of a 3D CAD model. This can be done in numerous programs, including NX, SolidWorks, and many more. Upon completion, the model is converted to an STL file that is able to describe the surface geometry of the part by translating it into a number of small triangles. The STL file is then sent to the ZPrint software. The 3D process allows full-color models to be produced, providing an aesthetically pleasing finish. The build software slices the part into layers 0.089 mm in thickness and sends it to the printer. The roller spreads a layer of ZP130 plaster powder over the build platform. The printhead then moves across and prints a layer of binder solution infused with coloured ink in the shape of the first layer. This binder solution glues the powder together in the desired shape. Any excess powder left unbound acts as a support structure for the part, much like the SLS process. The platform moves down a single layer thickness, and the roller then spreads another layer of powder across, thereby gluing it to the binder below. The printhead once again moves across and expels the binding agent in the shape of the next layer. This process is repeated layer by layer till the model is complete.
So you can really see the additive part of the additive manufacturing here. It's being built layer by layer. It's in the powder. And then what's pretty cool about this one, oh, you see one of the pieces fell off right here. They kind of glued it back on there. There you go, 3D printing process.
Design concept models and other small items.
This is pretty cool, I think. That's something that you can never machine. And that's really what the value of the additive manufacturing processes are. There's a way, since you're building it up level by level, there's things that you can make in the additive manufacturing process that you cannot do with machining. So that, I believe, is very, very interesting. Okay, let us continue on. See where I am right here. Let me go back. Make sure I'm in the right place. All right, I believe we did not look at this video just yet.
I'm Dr. Benasser, and my lab makes ears. The invention that we've discovered is a way to print living cells in a material that can be used to reconstruct tissues in the body. My laboratory is interested in regenerating cartilage wherever it's found in the body. The process starts with a scan of an ear. We sit someone down in a chair, and we have a camera that spins around their head and takes a 3D image of their head. Then can very precisely map out the topology of the ear. The next kind of key step is developing the ink for this printer. This ink is actually a living ink. It contains living cells. It's alive when we put it into the printer. It's alive when it comes out of the printer. The real power of the printing technique is that it can be used to make geometries that you just can't make with any other technique. You can make parts with holes in them. We can layer and cover and put different cells next to each other to create really the complex organs that make up our bodies. And after 2 months in an incubator, the tissue fills in and looks white, just like real cartilage. The implants that we're making are not rubber or plastic. They are alive. They grow inside the body or out. And this has a whole host of advantages over conventional technology. The body accepts these materials like it's part of the body because it is. Our long-term goals are to change the way that clinicians practice, to give them the next generation of implants that will be more successful, more like real tissue that will last in the body for decades.
So I showed you that video because I thought you'd like to see an interesting application of 3D printing. So in that case, the material was actually living cells instead of some type of plastic, some type of polymer, some type of metal. And so you do have a lot of medical and biomedical applications for the additive manufacturing for additive manufacturing as well. Okay, so nowadays 3D printing, of course, as I mentioned before, is used to represent most additive manufacturing processes, and there's a plethora of different things now that are being made by the 3D printing process. I'm not going to show you these entire videos, but we'll start, and if you're interested, please watch the videos on your own. They're going to be in our presentation that I'm going to put and post on D2L. But this is just to show you all the different types of materials that can be made by the 3D printing process. In this case, it talks about 7 mind-blowing things that are made by that 3D printing process.
HD to bring y'all 7 shocking things you won't believe were 3D printed. If you're unfamiliar, 3D printing is the process of making 3-dimensional solid objects from a digital file. It's an additive manufacturing process where an object is created by laying down layers and layers and layers and layers of material until the entire object is created, like this fiddle.
Okay, so we have lots of fun things being made by the 3D printing or the additive manufacturing process.
Dave experimenting with his island, and he has a few kinks to work out before he holds his cup of coffee. You want your kid to be perfect and nothing to go wrong. You know, it is what it is. If we had not had the insurance, then there's no way Sean would have had a prosthesis.
Okay, so this is a video that talks about 3D printed prosthetics. So that's another application of 3D printing of the 3D printing manufacturing process. Now let's focus a little bit more on 3D printing or additive manufacturing for metals. That's where the latest technology is focused on, because metals really have that material and mechanical strength that you really want to build things that can really affect our society and really change how we live. This process here is called selective laser sintering, but there are a couple of names for it. You can also hear it called direct metal laser melting. And usually if you see something with laser or sintering or melting, then it's pretty much this process right here. So what does this process involve? And so you have non-metallic or metallic powder. So again, you have those powders there, and they are selectively sintered. So this is kind of a combination of 3D printing and also stereolithography. So you're going to have a metallic powder, and you're going to have a laser that's going to come down and sinter it just like you did with the stereolithography process. But now instead of using a UV cured liquid, you're using metal powder. And it does this in layers to create of course, to create a part. And then it's centered usually. So when I say centered, the laser actually allows those metal particles to fuse together. So that recalls us back to powder metallurgy. Remember how we use the powders, they were pressed together and then we put them in the oven to sinter them? Well, in this case, you have a laser itself bit by bit sintering those metal powders together. So you can have ceramic and metal powders that can be that can be created using this particular manufacturing process. Now you can also have binders sometimes put in as well to help along this process. And here's a diagram. I'm gonna make my head just a little bit smaller so you can see more of the diagram here. Okay, you can see how this diagram is very similar to the 3D printing process. You have some powder over here. This is where your powder is being delivered. This is your build right here. You have 2 pistons. One is lower and one is raised. And then there's some type of roller or something that smooths the powder over this side. And then instead of having a glue binder, which happens in 3D printing, you have a laser that centers the metal at a particular point and creates that part. So here's kind of like a detailed view of what's happening right here. You can use lots of materials for this process. You can use both materials that are not metal and both are metal, as well as ceramic. So we have ABS, we talked about that. That's a very popular plastic. PVC, nylon, polyester, these are all very popular 3D printing or very popular additive manufacturing materials. You can also use wax, that's more like a rapid prototyping material, as I mentioned before, but also metals and ceramics too. And I believe I had a video, so let me see if that video still works here.
Direct metal laser sintering, also known as DMLS, is an additive manufacturing technology that creates metal parts directly from 3D CAD data without the need for tooling. DMLS utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and Inconel, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes, high-temperature applications, and end-use parts. The DMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data and mathematically slices it into 2D cross-sections. Each of these sections will act as a blueprint, telling the DMLS machine exactly where to sinter the metal material. The data is then transferred to the DMLS equipment. A recoater assembly pushes powdered metal material from the powder supply to create a uniform layer over the base plate. A laser then draws a 2D cross-section on the surface of the build material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised from the cartridge and recoated evenly upon the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength, fine features, and overhanging surfaces. The completed part is then removed from the base plate and treated with an age-hardening heat process to further harden the part. Any support structures are also removed at this time. With numerous surface treatment and hand polishing options available through service providers, DMLS parts can be used in highly cosmetic applications. Typical uses for DMLS include tools and manufacturing aids, small integrated structures, dental components, surgical implants, and aerospace parts.
Okay, let us continue on. So that's direct metal laser sintering, and then it's also called metal laser sintering and a few other things. But as long as you hear metal laser and melting, direct metal laser melting, I think is another one. As long as you hear one of those words in there, then you know that this is the process that it's talking about. Okay, now if you remember when we talked about fused deposition modeling, the guy also mentioned object, which is also called multi-jet or polyjet modeling, which is very similar to the stereolithography process. In this case, again, you have a photo cured liquid, but this time instead of having a laser, you have a print head deposit that build, and then you have UV bulbs that are right behind it that harden it. So instead of having a liquid vat, you have these extruder heads. They deposit the liquid, and then a bulb right behind it comes and then hardens it in place. So it instantly cures each layer, and that rising of that UV cured kind of layer there is deposited and in that kind of gantry extruder. Let's see here, where was it not? Get back to where I need to. Okay, here we go. So compared to the stereolithography, it doesn't need that post-processing curing like stereolithography might. So STL or SLA are both represent stereolithography. And also, if you remember, there is an SLA file in CAD where it cuts and sections it up. Guess where that comes from? Yes, that comes from stereolithography. And so this stereolithography process, it does need some post-processing curing where you take it out and you put it in the oven, but for object, it does not need that. And so it's a little bit shorter. And it also produces layers as thin as 6/10,000ths of an inch. So the layers are actually very, very fine as well. But of course, you still have that disadvantage of it being UV cured. And so it can be deformed when it's out in the sunlight or when it's exposed to certain UV lights. Here's a diagram of multi-jet or polyjet or objet as it's called. And you have your build material, of course, and your support material. Here are your print heads, and then right behind your print heads, guess what, is your UV curing lamp. Now you always have some type of leveling or a wiper or a roller to make sure that everything is even before you come back over it.
To take what's in your imagination and put it in your hands is pure magic.
It seems so out of this world.
You know, this can put manufacturing in a lot more people's hands.
PolyJet is amazing because of the type of quality that you get. You get really high definition, you get great surface resolutions, and you can have multiple parts in your hand within hours. It's the fastest technology that we offer.
PolyJet really shines with its surface finish and its ability to resolve very fine features.
The PolyJet process extrudes out or jets out a liquid resin that can be cured with a UV light.
They are made to react to ultraviolet light. And so that's the catalyst that causes these two separate components to come together to form the third, solid plastic component.
So with the PolyJet system, it jets out a thin layer of the photopolymer resin. It cures it with the UV light and then builds a cross section of that part layer by layer.
So after one cross section is deposited, the platform will drop down, allowing the gantry to pass with layer number 2, and then every subsequent layer after that. When the part has completed building, we will remove it from the platform.
So the parts coming off of this technology are really smooth. They don't require as much hand finishing and post finishing after.
Notice they still do require hand finishing and post finishing. So that really smooth is definitely relative.
So if you're looking for that amazing showpiece for a trade show, that's something that we can definitely accomplish in-house.
They say a picture's worth 1,000 words, a part's worth 1,000 pictures.
What we can do with PolyJet, there's just such a wide range in materials. We're printing hard plastics, and we're printing soft shore material, and we're able to make overmold pieces now where you're combining the two materials.
So like a drill that has a hard substrate and a rubber grip, you can build that in one piece.
As Stratasys Direct Manufacturing, having the engineering talent on our end to work with the engineering talent on the customer's end is really exciting because that's where the good stuff happens.
You get to be a part of someone's idea and then make that a reality.
And if we put those tools in their hands, we don't know what they're going to come up with. And that was just awesome. I can't wait to just kind of sit back and watch what's going to happen out of that.
Okay, so you can see that everybody is just really excited about their specific type of additive manufacturing process. And that's what normally happens in these really latest and advanced technologies that we're looking at here. Okay, so that was PolyJet or objet. Okay, and let's continue from there. Now, for our latest, we're going to talk about the latest printing in metal. And so you can look and see that there's several different companies out there, and most of them are doing some type of 3D printing technology. And when I say 3D printing, I mean three-dimensional printing in which they have a metal powder, and then somehow they're bringing that metal powder together, whether it's by glue, but if it's metal, it's most likely going to be by some type of laser. GE is using some type of electron laser, but if you look at Marco Forge, they actually have a unique answer to that in which they can print metal, but they're not using a powder. And so they have this machine called the Marco Forge Metal X. This is not a commercial for it, but what it is a combination of FDM and powder metallurgy. And so they do have a substrate or a line of metal material that's encased in a plastic wrapping, and it lays down that way. Okay, and then what they do is that they, after it's laid down, they take it and then they sinter it together. So it's a combination of FDM and powder metallurgy in that aspect. And they're creating, or they're printing metals, lots of metals, using this process without all that dirty mess of the powder and stuff. And these metals include copper, aluminum, steel, stainless steel, titanium, and Inconel. So they're printing metals that other people just are not printing. And so I just wanted to show you this because this is just a quick taste of what the latest is. And then after that, that would be the end of this presentation. Oops, let's go ahead and start at the beginning.
Hey everyone, I'm here to talk today about the Markforged Metal X process. It's a simple, safe, and cost-effective method to go from design to functional metal part. There are 3 steps in this process: printing, washing, and then sintering.
Gonna pause right there really quickly. So he's saying going from your design to an actual functional metal part, and that is a net shaped part, and it's talking about direct manufacturing in this case, which is kind of like the holy end all grail. But remember, there are some things that we still don't know about these products yet. We don't know how they're going to behave, and now after they've been in use for long periods of time, we're still trying to find that out.
First, let's start with CAD. You design your part, then export to STL and upload it to Eiger. Eiger is a cloud-based slicing and print management system that comes with every Markforged product. This automatically configures your part based on the material and printer you've selected. When your part slices for metal 3D printing, it gets scaled up to account for shrink and deformation in the downstream processes. It then slices your part into discrete layers, identifies overhang features, and builds supports and a raft underneath your part. As we go through printing, washing, and sintering, Eiger will monitor the part's progress along the way. Let's start this print and go to the Metal X. Before starting a print, the machine automatically maps and levels the bed to ensure the first layer goes down well. Your print is built of 2 materials stored in this heated chamber above, one of a ceramic release material and one of the metal to be printed. This filament material is metal powder safely suspended within a 2-part plastic binder. It gets heated and extruded onto the build plate where the part is created layer by layer. Release material gets extruded as an interface between the part and its supports. So once your part comes out of the furnace, it's easy to remove. Unlike other metal 3D printing systems, this process does not require loose metal powder, resulting in a safer and more cost-efficient workflow. 17.4 stainless steel is loaded now. However, with a quick changeover, the system is capable of printing in stainless steels, tool steels, coppers, Inconel, along with several other materials currently in development. Once your part is finished printing, you'll get a notification. At this point, you can go to the printer, remove the part from the build tray, and clear the bed. Now we have what's called a green part. It doesn't really look or feel like metal. However, a large part of it is comprised of metal powder. Next step will be putting it into wash 1 for the debind process. The wash 1 removes the first stage of the binding material. A green part is taken from the printer and placed into the wash basket, which is then lowered into the solvent. Wash times will vary, ranging from a few hours to a few days, depending on the thickest region of your part. After that, it's now called a brown part. It's ready for sintering.
All right, just kind of stop real quick there. Did you see just the wash went from a few hours to a few days? Okay, so still we have that limitation of these parts being made, taking just a long time to go through the whole entire process.
Let's go over to the furnaces. This is Sinter 2, a furnace designed for mid-volume production runs and larger printed parts. Sintering transforms a print from a lightly bound collection of metal powder to a fully finished metal part. First, the temperature ramps slowly to burn away the trace amounts of remaining binding material. Then, temperature ramps closer to the melting point of the material, allowing metal particles to start to fuse together to create a strong metal part. Markforged sintering furnaces use a carbon-free retort to ensure part quality and alloy composition standards are met for our finished pieces. Each run takes about a day and can be monitored remotely using the Eiger software. Once a run is complete, the setter tray full of finished metal pieces can be removed from the furnace. Once removed from the raft, these parts are ready for use. In the furnace, the layer of printed release material between supports and the raft and your printed part remains powderized. This allows the structure to be tacked to the raft to better control shrink and accuracy throughout the process, but also an easy release after sintering. At this stage, your part is fully sintered and ready to be used. It can be post-machined, polished, or otherwise processed as necessary for the final application, but in many uses, the accuracy and strength are good enough as is. It's ready for install. Check out markforge.com for more information about our simple.
Okay, I promise that is not a commercial for markforge.com, but if you want to find out more about that, then you can investigate as much as you want. And this is the end of the presentation, and thank you very much.